In this video, we are going to learn why we can't simply add two angular momenta using the components of their vectors. Then we'll learn the language of quantum mechanics and see how we can use it to add the angular momenta. We will also learn what some famous coefficients called Clebsch-Gordan coefficients are and how we can calculate them. Finally, we use all we have learned in practice to add two spin-half particles and find the matrix representations of operators and states in two different spaces. Suppose that we have a spinning top that spins in this direction. This is a classical kind of spin and can be characterized by a vector s in this space, which is along the top's axis. The rotation is counterclockwise, so based on the right-hand rule, the spin vector is upward. Curl the fingers of your right hand in the direction of the rotation, and your extended thumb points in the direction of the angular momentum vector. There is also another kind of rotation which is associated with the center of mass of the top. The center of mass is rotating around this axis. This rotation produces another angular momentum which is vertical in this direction. This kind of rotation is called precession that causes the top to wobble when it is spinning. We can find the magnitude of these two rotations by multiplying their moments of inertia around the associated axes with the magnitude of their angular velocities. The total angular momentum is the vector addition of these two angular momenta, and by knowing the components of these two vectors can be easily calculated. However, in quantum mechanics, we deal with a different situation in which we cannot actually know the three components of the angular momentum vectors. In fact, these two images are not accurate because the uncertainty principle suggests that we cannot know the three components of the angular momentum vector at the same time, meaning that we can't visualize a vector in 3D space. That is why you don't see lots of visualizations in quantum mechanics textbooks. Instead, in textbooks, you see some operators, some kets or eigenstates, some eigenvalues, and a lot of commutation relations. We use this formalism, this structure, to compensate for not knowing exactly how the different components of the quantum system are behaving at the time. Take this expression as an example. What is it saying? What are the different components? What do they mean? This one here is an operator. We call it J squared. It is a kind of abstraction that conveys a kind of concept in quantum mechanics framework. In fact, operators are generators of transformations that act on a space in which our states live. As you have seen so far, we have lots of operators, and in this video, we are going to focus on angular momentum operators, and J is just a representation of these group of transformations. These are kets. They are some vectors in Hilbert space and they represent quantum states. More specifically, in this example, these kets are the eigenstates of the J squared operator. It acts on these kets and gives the same state with a coefficient. This coefficient, which is a real number in this case, is called the eigenvalue of our operator. In other words, the result of a transformation that leads to the same state. Let's call this framework the language of quantum reality. These abstractions we are dealing with are the syntax of this language. So let's get to the concept of adding angular momenta in quantum physics. Suppose that we have two angular momenta in their subspaces of the Hilbert space. They have their own eigenstates, which are shown by kets, and also their eigenvalues, which are shown by some quantum numbers j and m. These two angular momenta may refer to two distinct particles or two different properties of the same particle. We can also write these commutation relations for the two subspaces. But keep in mind that the two angular momenta we are discussing here commute with each other. In fact, all of the components commute. We also know that the angular momentum squared and the z component commute. We have this set of operators that all commute with each other, so we can diagonalize them by the same ket. In fact, they can be expressed by the same eigenstates. These joint eigenstates can be written like this as a direct product or tensor product of the two eigenstates of the two subspaces. Let's use these operators on these kets to see how they behave. The angular momentum operator associated to the first particle or feature just act on J1 and M1. And the operators associated with the second particle or property just act on the second subspace J2 and M2. We also know that the eigenstates associated with each angular momentum is complete. So these new eigenstates also form a complete basis. The sum over M1 is from minus J1 to J1, and similarly, the sum over M2 is from minus J2 to J2. We can also see that these new eigenstates are orthogonal because they are the direct product of two kets that are orthonormal themselves. Pay attention that the dimension of J1 is 2J1 plus 1, and the dimension of J2 is 2J2 plus 1, and the dimension of these new eigenkets are 2J1 plus 1 multiplied by 2J2 plus 1, which is the product of the dimension of its constituent kets. This is because for each J, we have 2J plus 1 values for M in each subspace. Another concept we need to add two angular momenta is raising and lowering operators for each angular momentum. The first one acts on the M1 and the second one acts on M2. Now let's get back to the problem of adding these two angular momenta. This addition you see here is not adding two matrices because J1 and J2 live in different subspaces with different dimensions. But we found a joint eigenstate for them that can describe both of these angular momenta by the same ket. This spaces is called the uncoupled state in which individual angular momenta is treated independently. On the other hand, for the combination of these two angular momenta, we use another basis. It means that J and the Z component of J can be diagonalized using this basis, but it doesn't necessarily diagonalize the matrices for individual angular momenta J1 and J2. This basis is called the coupled basis on which the total angular momentum acts and gives a specific eigenvalues. These two bases are connected by the so-called Clebsch-Gordan coefficients that we're going to talk about later in this video. To find the kets of the coupled bases, we first need to find the commutation relations of the total angular momentum to see if we can find some other operators with which they have the same eigenstates and can be diagonalized at the same time. J has three components, and each component is the sum of the same two components of J1 and J2. Let's first find a commutator of Jx and Jy. Pay attention that these two components are associated with the total angular momentum, and what you see on the right expresses it in terms of the individual components of J1 and J2. We can expand it like this as you see. These two terms are zero because they belong to different angular momenta. The first term gives IH bar J1z and the last term gives IH bar J2z. So we have this commutation relation for Jx and Jy. Similarly, we can write the same relations for the other components. We also want to know how J squared commute with Jz, so we need to find it based on the two angular momenta we have. This can be done by simply finding the dot product, but be careful that we are using operators as the components and they might not be commutable. Expand these two terms based on their components. All of the terms are commutable because the commutation relation between different components of J1 and J2 is zero. So we can change the order of the operators that involve the same components and simplify the expression like this. Also, we prefer having raising and lowering operators instead of Jx and Jy, so the sum of these two terms can be written in the form of these operators. So, the operator for total angular momentum can be expressed as you see. The first thing you can immediately notice is that these two commutation relations are zero because J1 squared and J2 squared commute with all the components of the two vectors and also obviously with themselves. The z component of the total angular momentum also commutes with these three operators. But pay attention that J squared doesn't separately commute with the z components of the individual operators J1 and J2. Now we have a set of operators that commute with each other so they can be diagonalized using the same basis. These eigenstates are characterized by four quantum numbers J1, J2, J and Jz. and the eigenvalues of the corresponding operators can be written like this. For simplicity, from now on, we use just J and M and drop J1 and J2 because they are the same for all the kets. Let's review what we have done so far. We have two sets of bases for two different sets of operators, which are coupled and uncoupled bases. These are the eigenvalue relations for the uncoupled basis. This shows that these sets are complete, and also this relation shows that these kets are orthogonal. We can do the same thing for our coupled states, which are denoted by J and M. The dimension of both these states are equal to n, which is the product of the dimension of the subspaces of J1 and J2. It means that our kets will be n by 1 column matrices, and the operators can be represented using n by n square matrices. And now it's time to talk about Clebsch-Gordan coefficients, which are transformations that help us go from the uncoupled to the coupled basis. You can use the completeness relation of uncoupled states to expand the coupled bases. They have the same dimension, and for each basis of the coupled state, we have a linear combination of uncoupled state with some coefficients. These coefficients are called the Clebsch-Gordan coefficients. And we have n uncoupled states based on which the coupled bases are expanded. We know that both the coupled and uncoupled bases are normalized, so the transformation is unitary, and these coefficients are the matrix elements of an n by n matrix, which is unitary and preserves the norm of the state. Let's review some important properties of unitary transformations. Unitary transformations preserve the inner product of state vectors, and so it ensures the preservation of their norm. It's because in quantum mechanics, probabilities must be preserved under a change of basis. Under unitary transformations, the two sets of states remain orthogonal and complete, and they both live in the same Hilbert space. A unitary transformation has an inverse that is its Hermitian adjoint. It means the transformation is reversible and you can move freely between the coupled and uncoupled descriptions without any loss of information about the quantum state. There's a very important convention that takes Clebsch-Gordan coefficients as real. So from now on, these elements are all real, so they are equal to their complex conjugates. If you start from the orthogonality condition of coupled states and use the completeness relation for uncoupled states, we can write this expression, which can be simplified into this. And because our coefficients are taken to be real by convention, we can write them in this form. So we derive this relation for our coefficients that says each row of the transformation matrix is normalized. In fact, these coefficients are a row of our unitary matrix based on which we can expand, for example, row J and M, and each row is associated with a coupled state. If we take the sum of the square of these elements on this row, we must get 1. Now, this time, we start from the orthogonality of uncoupled states. Then we use the completeness of the coupled states, which is a sum over J and M, and we get this expression. It can be simplified in this form, in which we have again used the fact that the elements of our unitary matrix, which are the Clebsch-Gordan coefficients, are real valued. Particularly, we can use it in this form that says each column of the matrix is normalized. In this case, we are taking one of the columns of our matrix, which is labeled by one of the uncoupled bases. We can use the elements of this column to expand this specific uncoupled state based on the coupled states. And the sum over the coupled states gives 1 for each column. Before talking about calculating Clebsch-Gordan coefficients, let's take a moment and find the possible values for J and M, which are quantum numbers associated with the coupled states. What values can they get based on the quantum numbers for the uncoupled states? We know that the z component of J is equal to the sum of the z components of the two angular momenta we are adding. We also know that Jz acts on the coupled states and J1z and J2z act on the uncoupled states. The coupled states can be expanded in terms of the uncoupled states using Clebsch-Gordan coefficients, which we show by the symbol C. So we can write this equation, and on the left we use Jz, and on the right we use the ones associated with the uncoupled states. By using their eigenvalue equations, we can write this equation. So m is equal to m1 plus m2, and the maximum number of m is j1 plus j2, which are the maximum numbers for m1 and m2. We also know that the maximum number of m is j. So the maximum number of j is also equal to j1 plus j2. We know that for each j, we have 2j plus 1 number of states. So to find the number of all the states for j, we must sum over 2j plus 1 from jmin to jmax. Earlier we learned that jmax is j1 plus j2. Let's call the sum a. We can write this sum starting from the bottom once, and also we can write it starting from the top and going down. If we add the two expressions, we get a number of terms which are all equal. In fact, we have jmax minus jmin plus 1 terms. So we can calculate this sum in terms of jmax and jmin, and pay attention that jmax is j1 plus j2. So we find this expression that connects jmax, jmin, j1, and j2, and now we can find the value of jmin. Based on these calculations, the value of j minimum is the absolute value of j1 minus j2, and j can be equal or between these two values. The lowest value is the absolute value of j1 minus j2, and we increase by one increment to reach the highest value. For example, for two spin-half particles, there are two values for j, 0 and 1, or as another example, for the addition of a spin-half and orbital angular momentum 1, we have two values of half and 3 halves for the total angular momentum. If we can start with the z component operator and multiply it by both coupled and uncoupled states from left and right, we will have this expression which suggests that if m is not equal to the sum of m1 and m2, the corresponding Clebsch-Gordan coefficient has to be 0. But if m is equal to m1 plus m2, this element can be non-zero. These two expressions show which elements of our unitary matrix can be non-zero. They are known as the selection rules for the Clebsch-Gordan coefficients. Now, let's see how we can calculate these coefficients. Let me remind you that we are looking for these coefficients that connect the coupled and uncoupled bases using these coefficients that form a unitary matrix. And we also came up with these selection rules that give us both the upper and lower bound of j and also the elements that are non-zero. Let's first consider this a specific case for which we have these quantum numbers. We can expand our coupled state based on the uncoupled ones. Because of the selection rules we have, the only element that is not zero for this row of the matrix is the one for which m is equal to m1 plus m2. There is only one element with this condition. And we also know that every row should be normalized, so this element must be 1. There is another similar limiting case. Pay attention that in this case j is equal to j1 plus j2, but all the m's have negative signs. Again, the only case for which our coefficients are not zero are the ones for which m is equal to m1 plus m2. In this case, it becomes minus j1 plus minus j2. And as we have just one coefficient for which this condition holds, it must be equal to 1, and all the other elements of this row of our unitary matrix are 0. Now it's time to calculate other Clebsch-Gordan coefficients. In the previous part, we calculated some of the coefficients to be 1, but we cannot do the same thing for all the coefficients and we'll need a method to generate them. When the raising and lowering operators of the total angular momentum act on the coupled states, they increase or decrease the quantum number m by 1 unit. So using them between these two states and acting them on the right, which is the coupled state, gives the Clebsch-Gordan coefficients. We can also act these operators on the uncoupled states. And here we need to use the operators associated with the uncoupled states. So when these operators act on the uncoupled states, they give two terms, one of which increases or decreases m1, and the other changes m2 by 1 unit. Now we want to use these operators on the left, which are the uncoupled states, and we get another expression that involves Clebsch-Gordan coefficients. These two terms must be equal because it doesn't matter whether we use the step operators on the right or on the left. Finally, to calculate these coefficients, we have found a recursion relation that connects different elements of our unitary matrix based on quantum numbers we have for both the coupled and the uncoupled states. Now, as an example, we are going to see how we can add two spin-half particles. You can consider a hydrogen atom in the ground state for which the orbital angular momentum is 0 and the two spin-halves are the spins of an electron and a proton. There are four uncoupled states that we have constructed using the two spin angular momenta, which are both half and fixed, and also two associated magnetic quantum numbers m, which can be either half or minus half. We can also show these eigenstates using up or down arrows. The four states are up up, up down, down up, and down down. This is just another way of representing the uncoupled states, which is also considered as an informal one. For the coupled states, we know that the total quantum number for angular momentum is between these two values. So the two possible values for S are either 0 or 1. We can show these coupled states using quantum numbers S and M, and when the operator associated with the Z component of the angular momentum acts on these kets, it gives M times H bar. We are looking for some coefficients by which we can expand the coupled states in terms of the uncoupled states. These coefficients can either be shown by the inner product of the coupled states with the uncoupled states, or a symbol like C that connects the two frameworks. So, using all the information above about operators and states in these two frameworks, we can also write the eigenvalue equation in terms of m1 and m2. It shows that m is equal to m1 plus m2. And the values of m for these four states are, as you can see below each one. Pay attention that we have two 0m's, and you'll understand why in a moment. So these are the four coupled states associated with the addition of two spin-half particles. And now we need to find the coefficients that relate these two spaces. In fact, we are looking for a 4x4 unitary matrix that gives the coefficients of the four coupled states in terms of the four uncoupled states. We can expand each of our coupled bases based on the uncoupled states. We are looking for these coefficients. For example, we can write this coupled state in terms of our four uncoupled states with their associated CG coefficients. But three of the terms are 0 because for each of them m is not equal to m1 plus m2. So this is the only non-zero element. These two states are both normalized, so the coefficient must be 0. With the same logic, we can write this coupled state based on just one uncoupled state, and we get another state to be 1 and three other elements of our unitary matrix to be 0. We can act the lowering operator on this state, which is equal to one of the uncoupled states. We use S minus for the coupled states and the sum of two lowering operators of the uncoupled ones. Using this relation, we can act the lowering operators on the kets. And we have another state which has two terms. Pay attention that for both terms, m is equal to m1 plus m2. Pay attention that if we act the raising operator on this state, it yields 0. We expect to find the same state if we act the raising operator on the coupled state 1 and minus 1. Also, acting the lowering operator on this state gives 0. As we expected, we'll get the same linear combination of uncoupled state for this ket by using the raising operator, which increases the quantum number m by 1 unit. So far, we have found three of the four coupled states in terms of our uncoupled ones. They are called the triplet states. The total spin is 1, and we have three possible numbers for m, which are minus 1, 0, and 1. There is another state left, which can be written as a linear combination of these two uncoupled states. We know that it's normalized, so a squared plus b squared has to be 1. It is also orthogonal to all of the triplet states, specifically to this one. And writing the orthogonality condition and considering the fact that a squared and b squared is equal to 1, we can find a to be 1 over square root of 2 and b equal to minus 1 over root 2. Now we have all the uncoupled states, and the last one we have just found is called the singlet state. We can write these four equations using matrices. There are two column matrices whose elements are the coupled and uncoupled states, and we have a 4x4 matrix, which is the unitary matrix that transforms the coupled and uncoupled states. Let's talk a little bit about this transformation matrix that we know is unitary. That's because multiplying it with its adjoint, meaning that if we change the rows and columns and take the conjugate of the elements, we should get the unit matrix. Each row of this matrix has the same S and M, and each column has the same M1 and M2. As you can see, each row and column of this matrix is normalized, meaning that if we take a row or column and add the squares of the elements, we always get 1. We can use the adjoint of the transformation matrix, which is equal to the inverse of this unitary matrix, to write the uncoupled states based on the coupled states. And this is how we can go from the coupled states to the uncoupled states. Pay attention that if we change the order of two of the coupled states, the transformation matrix changes and we have to change two rows with each other. So in our new matrix, the last row represents the ket 1 and minus 1. We can use this expression to find the matrix elements of the Z component matrix. There are only two non-zero elements in this matrix, as you can see. Pay attention that the third row and column correspond to the ket 1 and minus 1, which gives h bar m for the eigenvalue. We can also express this operator using the uncoupled states as the sum of two individual operators. Again, we have two non-zero elements for the diagonal elements for which the sum of m1 and m2 is not 0. Pay attention that the element minus 1 in this matrix is associated with the ket down, down. We can use the unitary matrix to transform the operator in coupled bases to its counterpart in the uncoupled bases. First multiply the first two matrices, and with multiplication with the third one, we have this operator in the uncoupled basis. Now take a look at this expression. We can write S1Z as the outer product of the same operator in the two-dimensional Hilbert space in which we just deal with one particle with a unit matrix which represents the two-dimensional Hilbert space for the second particle. We can do the same thing for S2Z, for which the first 2x2 matrix is associated with the Hilbert space of the first particle, and the second one is the matrix representation of the Z component of the spin angular momentum in the second Hilbert space. They both give two 4x4 matrices that we use for addition of two angular momenta. So by simply adding these two 4x4 matrices, we can find a matrix representation of total angular momentum in the uncoupled state. Again, by using the unitary transformation matrix we derived, we can move to the coupled basis. In the next video, I'm going to do the same thing for a spin half and a spin 1 particle.